Hi everyone, here we go. It's Bronsted-Lowry Acid Base Theory, and this is one of my favorites. Can we move the bubble? Perfect. Okay, this is one of my favorites. When I was in high school, I hated it, but now I have a lot of respect for it. So my assumption is that it's going to stink at first, but after a while, you'll learn to love it. So there was this team of scientists. Their names, I don't remember their first names, but their last names were Bronsted and Lowry. And they were looking at a sample of ammonia. Let me get my pointer. Okay. Sorry, you're propped up on a tissue box here. Ammonia, if you were to do a pH test on ammonia, its pH usually comes up somewhere between 8 and 9, meaning that ammonia is a base. But if you look at the formula for ammonia, nothing in the Arrhenius theory says that that's a base, because Arrhenius said bases have OHs on them, right? Well, if bases are supposed to have an OH, then how is it possible that ammonia has a basic pH? Well, these two guys, Bronsted and Lowry, said it's time to change or update the definition because now we know more. So they came in and said, if we took ammonia and we dissolved it in water, the ammonia kind of forces the OH to come off of water. There's still an OH here, but it doesn't come from ammonia itself. Ammonia is going to steal a hydrogen off of water, and then water is going to be left as an OH, which is where the Arrhenius OH comes from, if you're catching my drift here. So we have the Arrhenius definition, which is kind of like narrow, and then Bronsted and Lowry come in and say, you know what, we need to expand this definition and make it a little bit more succinct. So we need to update the definition of an acid and a base, which is where they come in. So they have decided that bases are going to be compounds that accept hydrogens, or in other words, steal them. So ammonia steals a hydrogen from water, or water gives up a hydrogen to ammonia, who then accepts that hydrogen, and then you'd be left behind with the OH, which would kind of sort of go with Arrhenius. It's just a technicality of where the OH comes from, really. So something I would like to note here is that hydrogen is usually a proton and an electron. Okay, so it's a positive and a negative. But if we dump that negative and we look at just H+, just a positive hydrogen, that's also just a proton. So hydrogen and proton are going to be used interchangeably here. And it is all throughout acid-base chemistry. It's a hydrogen ion or a proton. They mean the same thing. So here, your bases are going to be accepting of that hydrogen or of that proton, where on the flip side, an acid is going to be the one who donates. Oh, I did it a second time. I copied and pasted and it doesn't respect my subscripts. Irritating. So acids are going to donate your hydrogen. Oh, I lost the pointer. Oh, goodness gracious. There we go. So acids donate their hydrogen. So if we look at HCl, for instance, which we already know is an acid based on the Arrhenius definition, this is going to donate or give up its hydrogen to create H3O+, which we have learned from Arrhenius is called protonated water, and that's where the H+ goes floating around, right? So there's like a cute little thing to remember this. Bronsted-Lowry theory is bad. The bases accept protons. I'm sorry, that was so cringy. Which is also a hydrogen ion, and then acids will donate those protons or hydrogen ions. Bases accept and acids donate. Now, I have a little trick for finding your acid and your base when you're given an equation, something like ammonia that doesn't, like, there's no Arrhenius definition to rely on. You have to solely rely on the Bronsted-Lowry definition. Here's what you do. You split your chemical equation in half so that your reactants are your before and your products are your after. I think this is backwards for you, but that's okay. You're going to find the pairs that look similar, and then you're going to figure out where the proton is going. So in this example, we have H2SO4 and H2O. This is going to become hydronium, H3O+, and a hydrogen sulfate ion. So in this, we're going to circle the things that look similar. So in my pink circle, I have H2SO4 and HSO4. Those are close enough. And then we have our H2O and H3O+. So I think you can kind of gauge what's happening here. We have our hydrogen, the sulfuric acid is going to lose an H to become HSO4 minus. So in doing that, it had to lose an H, which would kind of fit into donating an H, which would make this an acid, which you already know because Arrhenius says that this is an acid. But here's kind of the weird thing. Water is gaining a hydrogen. So in this case, water is accepting a hydrogen to become H3O+, which means that water is acting as a base. That would make this its conjugate acid. Acids and bases come in pairs. If this is our acid, then this would be the conjugate base. But we don't need to worry about that for Regents level chemistry. That is honors and AP and college chemistry type of things. But for us, if we are just looking at identifying what is an acid here, this H2SO4 is going to be an acid because it has donated a hydrogen. It's lost a hydrogen in order to become HSO4 minus. And as weird as it sounds, it's true. Water here is acting as a base because it has accepted a hydrogen. Now, water is just going to be a weak base because this is a strong acid. Strong acids and weak bases are going to pair together. We always have a strong and a weak paired up. So that's what's going to happen here. Because this is a weak base, this is our strong acid. They're always going to pair one strong, one weak, one acid, one base. That's pretty much it for Bronsted-Lowry theory. It is, there's your base and there's your acid. It's not as scary as it sounds. Your bases accept protons, which we also call hydrogen ions, and your acids are going to donate them. So acids give to bases. And in order to find the pair, we look in our chemical reaction, we split it into a before and after. Find the things that look similar, determine what has happened with those H's if they're gaining or losing, and then remember that bases accept and acids donate. That's it. That's Bronsted-Lowry theory in a nutshell. I think it's one of those things that you learn best by practicing. So that's all. Just leave me a comment if you have any questions, and I'll do my best to get back to you.